In many scientific fields, we encounter data that grows exponentially across multiple variables. While these curves look beautiful, they are notoriously difficult to analyze and solve directly using standard linear regression or simple algebraic techniques. To make these problems manageable, we use a technique called logarithmic linearization. By transforming the exponential equation into a linear one, we can easily identify growth rates and initial values using the properties of straight lines. Consider a model where growth depends on both time and an external factor, like scale. Here, p represents our result, which is influenced by an exponential time component and a power law scaling factor. The key to unlocking these equations is the natural logarithm. Remember these two rules: the log of a product is the sum of the logs, and the log of a power allows the exponent to move to the front. First, we apply the natural log to both sides of our multivariable equation. This allows us to break the complex product on the right side into a series of individual logarithmic additions. Next, we simplify. The ln and e cancel out, leaving just a rt. The exponent k drops down in front of ln, s. We have successfully transformed a product-based curve into a sum-based linear equation. Notice the structure: this is now in the form y equals c plus mx. If we plot the natural log of our data against time, the slope of the resulting line directly gives us the growth rate, r. Let's apply this to a real-world example. Suppose a bacterial population grows based on time and nutrient density. We need to find the linearized value of the population after 10 units of time. We plug our known values into the linearized formula. The natural log of 100 is approximately 4.605. We multiply our rate by the time of 10 and include our nutrient scaling factor. By calculating each term, we find that the natural log of our population is 10.892. This linear value is much easier to use for further statistical analysis than the original massive exponential number. To find the actual population count, we simply take the exponential of our result. By raising g to the power of 10.892, we find that there are approximately 53,744 bacteria. When dealing with 3 or more variables, linearization allows us to use multiple linear regression. This treats each variable as a separate additive component, making it possible to solve for several unknowns at once. A major advantage of the linear form is that errors, or residuals, are much easier to see. On an exponential curve, small errors at high values look huge, but in log form, they are standardized. Be careful! A common mistake is forgetting to take the log of the initial constant, p0. Also, ensure you stay consistent. If your growth uses e, use the natural log, not log base 10. To summarize, start by applying the natural log to the entire equation. Use log rules to turn multiplication into addition and exponents into coefficients. Solve the linear equation, and then convert back if necessary. Let's test your knowledge. If we have the linearized form ln y equals 2 plus 3 or ln x, what was the original exponential relationship? Think about how we reverse the log rules. The correct answer is B. The constant 2 becomes the exponent of e, and the coefficient 3 returns to the exponent of x. You've mastered the basics of logarithmic linearization. Linearization is a powerful tool that turns complex growth into clear, actionable data. Use it to simplify your multivariable models and unlock deeper insights. Generated by Vision Solve AI.